anyhow, we're going to try to get a little caught up today and do two things as long as my voice lasts. One is talk a little bit about how a spectrometer works, and then start to talk more about experiments that people use in solution for assignments of proteins. And we'll just see how long my voice lasts. So here's kind of a block diagram of what a spectrometer has to do. So you all know there's a magnet and a probe. And of course, there are shim coils and then the lock to stabilize the field, at least in a solution machine. And then the RF is generated by a pulse programmer that executes the pulse sequence, frequency synthesizer that generates the RF waveform, and then an RF transmitter that's basically the amplifier that amplifies the pulse up to whatever strength you want. And then on the receiver side, there's a preamplifier, the phase-sensitive detector, filters, and then the ADC converter that digitizes the signal so it's stored on the computer. Over the last couple of years, well, really over the last 20 years, this kind of classic picture has been changed in some ways. I think these are things I've said. These days, if you buy a Neo console from Brooker, everything listed in the RF and receiver module is on one board, which is really kind of remarkable achievement. And that means basically that every channel on the spectrometer is capable of detecting the free induction decay. So if you're applying carbon pulses, you also have a receiver for carbon. If you're applying hydrogen pulses, you have a receiver for hydrogen. They're all present and can be active at the same time. So they're experiments mostly for small molecules in which two nuclei are recorded at the same time. But those experiments really haven't taken off in proteins or nucleic acids because you're really running two independent experiments. And as a result, your starting magnetization tends to get split between the two experiments with lower signal to noise. So there's a capability in the machine that we really can't take very much advantage of yet, which also suggests something for graduate students and postdocs to think about how we might use this capability that happens to exist. Now, why would I bother to write that there are audio filters? Anybody have any idea why we care?
What was the question? Sorry.
Pardon?
What was the question again? Sorry.
Why do I highlight audio filters? Seems like maybe a detail.
Is it to prevent aliasing of peaks in the direct dimension?
Well, it's not so much alias peaks as it is alias noise. Noise, noise has a really wide bandwidth. When people talk about white noise, they mean noise at every frequency. And if we do a Fourier transform, all of that noise outside of our spectral region is going to fold, it's going to alias into our spectrum, and noise would just swamp the signal. So the audio filters have to cut out all signals outside of a certain bandwidth. That has to be bigger than our spectral region so that we can accurately measure the spectral region of interest, but not too wide because then just more noise aliases in. Back when I started doing NMR, the design of audio filters was a big topic because filters have an effect on amplitude and phase of a signal that goes through them. And obviously, amplitude and phase are really important to us in NMR, particularly phase. But these days, it's a little less critical because a modern spectrometer sets the audio filters pretty wide and then uses a digital filter to finish the job. And digital filters, since they're not built out of real electronic components, can be designed to have much more ideal properties. So really now there would be an audio filter, and then part of after the ADC, there would be some digital filter process going on. But this in practice is really important because of the properties of noise and the aliasing of the signal by the Fourier transform. It's a boring picture. It used to be one could open up a solution probe and look at it. But now with cryoprobes, you can't open it up. But an old room temperature probe would basically look like this. There's a coil, usually two coils on modern probes that are physically arranged to be as orthogonal as possible. And then they're tuned for the nuclei that you're interested in applying pulses to. So on a solution triple resonance probe, if it's a so-called inverse probe or proton detect probe, the innermost coil, the one closest to the sample, will be tuned for hydrogen and then deuterium, because deuterium is the most common lock signal for solution NMR. And then the outer coil would be tuned for carbon-13, nitrogen-15. If it's a quadruple resonance probe, the outer coil would then be also triple tuned for phosphorus. There's an inner and outer coil, again, to try to isolate them from each other. That not only are they arranged to be more or less orthogonal to each other, but also having them spatially separated helps keep them independent of each other. But in almost all probes, if you have the choice, the spin type that you're detecting, you like to have on the inner coil. So for example, at the center, we have probes. Most of the probes have hydrogen on the inner coil, but there is a cryoprobe where the inner coil is tuned to carbon or nitrogen, and the outer coil is hydrogen, in case there are experiments where you want to detect carbon directly. So again, anyone know why this matters?
Signal to noise,
Pardon?
signal, intensity.
Right, why should it matter which coil you use?
The proximity will affect the flux through the coil, and so it will affect the signal intensity.
Oh, so there's something called the filling factor, and basically the more of the coil occupied by sample, the more sensitivity you have. So the inner coil has the most filling with the sample. The outer coil, by definition, has more empty space. So the signal to noise depends a lot on the filling factor, and it's a pretty big effect. The difference between a probe with carbon on the outer coil or carbon on the inner coil is on the order of a factor of 2 to 4 more sensitive if the tuning is on the inner coil. So it's a pretty big effect. And then there's circuitry here. There's these little coils and things are for tuning. And tuning a probe is not much different from tuning a radio. So, on a radio, you adjust the tuning to find the right station. And when you dial the knob on a radio, you're adjusting some capacitors. And when you're tuning a solution NMR probe, you're also adjusting some capacitors with the same idea to make the circuit resonant with the frequency that you're trying to irradiate the sample with. But then you might know you also match if when you tune. And matching you don't normally do on a radio. But if you look on the back of like a stereo speaker, you'll see that there's something that says like 50 ohms. And that means that the speaker is designed to have an impedance of 50 ohms. And therefore, it should be connected to a radio or a stereo whose output has an impedance of 50 ohms. So there's this theory in electronics that you can only transfer signal between circuits if their impedance are matched. And if their impedance aren't matched, you get inefficient transmission and reflection of the signal back to the source. A radio can be built with a fixed impedance, but you can't do that with a probe because the impedance inside the probe is the impedance of the probe plus the sample. So depending on volume of the sample, solvent, salt, etc., the matching has to be done each time because sample plus probe has to be matched to the RF transmitter. Otherwise, pulses will be very inefficient. On most solid state probes, there's only one coil. So everything is multiply tuned. But otherwise, tuning and matching is basically the same idea. In a cryoprobe, built into the body of the cryoprobe and also cooled, is the first stage of the preamplifier. On a room temperature probe, the preamplifier is only the thing sitting on the floor. So you may have noticed sitting on the floor next to the magnet is a preamplifier housing that has slices for different nuclei. For a cryoprobe, that's a second stage amplifier. And the first stage preamplifier is in the base of the probe where it's kept cold. And this again goes back to some basic electronics that after the first preamplifier stage, any more amplification that we're doing is just amplifying the noise and signal that's already been through the preamplifier. So one wants to get the first amplification as close as possible to the coil of the probe. And probably just for historical reasons and difficulty, the first preamplifier stages were never built into the body of the room temperature probe. But for the cryoprobe, that turned out to be essential because the noise in the coil and preamplifier is dominated by Josephson noise. Anyone know what Josephson noise is? It's just the noise from the random motion of electrons in the metal of the coil or in the electronic components of the preamplifier. And the reason a cryoprobe works is that random noise depends on temperature. So you lower the temperature and the amount of Josephson noise goes down. But it's important then that both the preamplifier and the coil be kept cold, because if the coil was cold but the preamplifier was at room temperature, you would end up with a mixture of the amount of noise from the cold coil and the warm preamp. So cooling the preamp, even if it's not quite as cold as the coil, is really helpful. But anyhow, because of all that, you can't really open up a cryoprobe and look inside and see what it looks like. Yeah, so a solution cryoprobe keeps the coil and preamplifier to about 20 Kelvin. And it's pretty remarkable engineering because the 20 Kelvin coil has to be very close to the room temperature sample. Otherwise, filling factor would defeat the advantage of having the cold coil. So it's really pretty remarkable engineering that this can be done. So I think maybe we talked about the sampling theorem. Anyone remind me? So the sampling theorem says that if we digitize a signal, which of course is what the spectrometer does, and we have the signal digitized in uniform steps with some value, sample time delta t, which is how the spectrometer works, then the Nyquist theorem says that the largest absolute value frequency that is sampled twice per period is 1/2 times delta T. And that means that the spectral width, since we have positive and negative frequencies, is 1/delta T, and the spectrum covers the range minus the Nyquist frequency to plus the Nyquist frequency. As we already said, everything outside that frequency range is aliased into that range, so appears artifactually. That's somewhat of a detail. So for frequencies outside, almost all the way you detect now regards the signal as complex. And in that case, for aliasing, it looks like the edges of the spectrum are connected in a circle, so that a signal that is a little bit outside the left edge of the frequency range will appear a little bit inside the right-handed region of the range, so that we can always calculate where the aliasing goes for individual peaks. But obviously for noise, that doesn't make any sense. The noise is everywhere. And here's just a simple picture. So the black sinusoid is sampled at the Nyquist frequency, and then the dashed sinusoid is a higher frequency. And you can see that the dashed line I designed to go through exactly the sampling points of the black line. So if this is our sampling, we can't tell those two signals apart. They're going to appear at the same part of the spectrum, even though the one is at much higher frequency. If we want to detect accurately the higher frequency, we have to sample faster. This part clear? This is actually a pretty important detail of NMR spectroscopy. So then, of course, we're going to do a Fourier transform. But here's the continuous Fourier transform. But what we do in practice is a discrete Fourier transform. And this also has a number of consequences for NMR. First, the discrete Fourier transform is periodic, and that's why we get aliasing. And then it'll turn out that the transform signal is identical to the theoretical signal from a continuous Fourier transform only if our first data point is acquired with a time delay of 0 or 1/2 times the spectral width. There should be parentheses here. And acquiring a t=0 usually isn't so easy because, of course, we have pulses and we have to wait for the pulses to finish. It also has the consequence that there's no signal for t less than 0. And this turns out to mean that the data should always be zero filled by a factor of 2 before Fourier transformation. And I might have mentioned that I uploaded a paper that explains this very nicely in terms of the Kramer-Kronig relationship as to why you always have to zero fill by a factor of 2. You can zero fill by more, but that is really interpolation, not real information. So here is a typical processing schedule that one would see in NMR pipe, for example. And depending on this, what the initial time point was sampled at, the first point has to be scaled or not scaled. Typically, you apply a window function of some kind, zero fill by a factor of 2 or more, transform, and phase. If the initial time point is 0, there's no first order phase needed, only 0 order phase. And if the initial time point was set to be 1/2 times the spectral width, then 180-degree first order phase is needed. And again, particularly for data sets where you want to quantify the peaks, getting the absolute phase predetermined is, particularly in indirect dimensions, is really useful for having the cleanest base plane, which makes it as easy as possible to quantify the peaks. I think some of this is pretty simple that you can look at yourself about phasing and window functions. Here's just a picture of the effect of scaling the first time point incorrectly. And you get offsets in the base plane that depend on how intense the peak is. So this most often comes up in the T1 dimension. So in the future, when you have graduate students of your own and they show you a spectrum that has vertical stripes everywhere there's a strong peak, your first thought is that they scaled the first point incorrectly. So you can ask them, how did you scale the first point? Key. Yeah, because I think that's enough to say really about the machine. Oh, I should say one thing about phase sensitive detection. So we talked about how we have to measure both the X and Y magnetization in order to determine the size, the sign of the frequencies. And that's called quadrature detection. And in the old days, this was done again with electronic components that was called mixers, so that the original signal would be split in half, and then half mixed with a sine wave and half mixed with a cosine wave at the RF frequency or the detection frequency. And then the output from the mixers would go through a low pass filter. And then you would have the X component and the Y component that could be combined in a complex signal. And again, that's done differently, say on a neoconsole. One reason this scheme was thought up was because in the beginning, analog to digital converters were slow and had limited number of bits of signal they could digitize. So that this scheme of splitting the signal and put it through these analog electronic devices, the splitter and the mixer, were a way of minimizing the frequency range that the ADC actually had to accurately digitize. Nowadays, and then there are problems with balance between these two channels because the electronic components couldn't be the same, obviously, because of manufacturing variability. So then there'd be problem with balance between the channels and that meant one had to use phase cycling to balance out the channels. But now ADCs are much faster, and this quadrature detection can all be done in one swoop and by digitizing the whole spectral width. And this is called digital quadrature detection on a Brooker. And if you are doing kind of normal proton experiments, you'll normally have the digital quantum digital quadrature detection turned on, but there's an option to turn it off and go back to the old way, because if you pick some enormous bandwidth for your spectrum, then you'll run into the limits of the ADC converter, and switching to the original way gives you basically a factor of 2 larger bandwidth that you can digitize at the downside of having to make use of these analog devices. And probably at some point that will just disappear as an option on a spectrometer. That's kind of a quick run through of how a spectrometer works. Again, in the old days, one worried about this a great deal because basically the spectrometers barely worked, and you had to know a lot about how they worked to get your experiments done. And fortunately now, particularly for solution NMR, the spectrometers work very well, and one doesn't worry so much about what happens under the hood. And even if things go wrong, there's not much you can do because everything is so digital, other than get a new board from Brooker, as opposed to getting out a soldering iron and doing anything. So any questions about that quick tour? All right, so I'm going to start to talk then about experiments in solution, with the first emphasis on how do you get assignments. So this is introduction. You see, one, of course, starts whether it's nucleic acids or proteins with the sequence of the molecule. So here's ubiquitin. There's a sequence, and here's just a tabulation of how many of each type of amino acid it has. Because as we do the assignments, for example, we're going to have to make sure that we end up with 2 alanines and 6 glycines rather than 5 alanines. So we can't start from 0. We have to at least know the sequence. And of course, fortunately now, one knows sequences from gene sequencing, although there can be issues with post-translational modifications in some instances. Probably you're unlikely to assign a macromolecule these days with only one H NMR. Almost always now we do some labeling, but if you do, the historic way of assigning unlabeled molecules was to, within a single spin system, basically an amino acid or a subset of the nuclei in the amino acid, linked together using cozy and toxy, all the spins that were connected by 3-bond J couplings. And the problem then is there are important linkages where there aren't large enough J couplings. There's no 3-bond J coupling that links two spins. So for example, if we want to link amino acids together in a chain, then we would need, for example, a scalar coupling between the alpha hydrogen of one amino acid and the nitrogen, the amide nitrogen amino acid of the next amino acid, so that we can reach across the peptide bond. But those scalar couplings are way too small to be useful. So you end up from the cozies and toxies with a set of essentially amino acids, but you don't know their order. And then the order is put together by looking at distances in nosy spectra. And the main problem that happens here, of course, is the nosy spectra depend very strongly on the structure. And if you're trying to do the structure, then there's a kind of circular reasoning in getting the sequence-specific assignments. And if people make a mistake in doing that, that has a huge effect on the structure. And with labeled molecules, the situation gets much easier because we can usually link together large number of spins by transferring through relatively large carbon-carbon couplings, and then use experiments in solution like HNCA and HNCOCA to connect amino acids across the peptide linkage. So we don't have to rely on nosy spectra to get the assignments. And in solid state, the approach is quite analogous, except instead of using the scalar J couplings, you'd be using the dipole couplings. So you've seen pictures of ubiquitin spectra. We've talked about the cozy. We talked very little about the toxy. I just kind of said it exists. And the idea is to use some designed RF pulse train so that the Hamiltonian looks like the scalar coupling, strong coupling Hamiltonian, so that the effects of chemical shifts are scaled down far enough that we're in the scalar coupling, strong coupling limit, and then magnetization can transfer through the whole spin system. And there's a variety of different pulse schemes to do this. For just conventional solution NMR at moderate fields, DIPSY is probably most popular. Flopsy has somewhat better performance, as you can see here. But as you get to higher and higher magnetic fields, these require stronger and stronger RF fields. And then there are various kinds of adiabatic pulse schemes for trying to do the toxi transfer. And this worst two is one. I mean, the profile doesn't look as nice as here, but it can be used with very large bandwidth. But it does become an issue at 1.2 gigahertz for solution NMR, how to get these isotropic mixing schemes to work, because the chemical shift range becomes so large, and then for TOXI to work, the pulse sequence has to scale down the chemical shifts, and that's obviously harder with a bigger bandwidth. And then I might have actually showed you this picture already for how you pick the mixing time, because the magnetization transfers in rather complicated ways. And here's transfer for the isoleucine side chain, and the dashed line here, for example, is transfer from the alpha to the beta, and then all that magnetization leaches out to the rest of the side chain. And you can see you get a lot of magnetization to build up on H gamma 2, which of course is a methyl group, and then the rest kind of spreads out. Whereas if you do this in water, then you see a very different profile. Here's then you have transfer from the amide hydrogen again to the alpha, and then the magnetization goes out through the rest of the side chain. And as said here, mostly mixing times of about 45 and 70 milliseconds are used, kind of 45 to get this initial transfer, and then 70 to get out into this range. And for proteins, it's hard to use, sometimes even 70 because of relaxation losses. Small molecules, people can use much longer mixing times, but for proteins, it's hard to go beyond 70. And there's just some pictures that you've seen before. We've talked about the nosy. And we've also talked already about the HSQC experiment. And again, this is part we showed previously, breaking this into blocks and then analyzing each block, recognizing an inept block here, a block that does frequency labeling while decoupling, and then a block that does a reverse inept. What I wanted to talk about, though, is further. So in particular, I want to talk some about these two pulse sequences because they're building blocks of a lot of solution NMR experiments. The first is called a sensitivity enhanced HSQC. The PEP means preservation of equivalent pathways. And then here is a sequence you can see that looks pretty similar, except it generates a TROSY experiment. Now, recall here for this inept, at the start of T1, we're going to have antiphase S-spin magnetization. And during T1, that's going to split into one component. If this pulse was an X pulse, let's assume phi 1 was X. Here we have 2I minus 2IZ SY. And at the end of T1, we're going to have minus 2IZ SY cosine omega ST and 2IZ SX sine omega ST1. So we're going to have the cosine and sine modulated component. In the normal HSQC, the second pulse, for example, puts the S magnetization on Z for one of those components, and then we refocus it to observable proton magnetization. So we detect either the sine or cosine and component, and the other component is lost to us. And as a result, we lose half the signal. We run a second experiment to pick up the other component. We have our quadrature pair. What this experiment tries to do, what the PEP HSQC experiment tries to do, is recover that second component. And what happens if you go and work out the product operators is during this period here, while one component is refocusing to hydrogen, this other component is just multiple quantum coherence, a mixture of zero and double quantum coherence. But there's no further chemical shift evolution because of these pulses. There's no J coupling evolution because there's no J coupling for zero and double quantum coherence. So here we would have generated some multiple quantum state. Here we have that same state. So instead of turning on the receiver as normal, we've refocused the magnetization, and now we store it on the z-axis, where relaxation is relatively slow. And then the rest of this sequence transforms that multiple quantum coherence back to proton, and then the final pulse rotates the proton magnetization that was stored on Z into the transverse plane, and now we have both components, the sine component and the cosine modulated component. So we've recovered twice as much signal. Unfortunately, they're mixed together, and to unmix them requires a second experiment. And since we have two experiments, the noise goes up by a factor of √2. So we have double the signal, the noise goes up by √2. So we gain, ideally, a factor of √2 in signal to noise. Minus, of course, some relaxation during this extra period. So you don't get quite √2. I thought this experiment up. They were the papers describing the sequence were some of my first papers as a postdoc doing NMR. And in the beginning, nobody believed us that this worked. And one reason they didn't believe us was that we've added 180-degree pulses. And you'll recall when we were talking about pulses, we said, 90-degree pulses work pretty well, but 180-degree pulses have huge resonance offset effects, etc. So people just didn't believe that we could add 180-degree pulses plus a couple more 90s and gain √2, that we would have lost more signal by adding the pulses than we would gain from keeping the other component. And despite the fact that we showed in the paper that we could gain almost √2, people just somehow thought we were collecting twice as much data. And eventually, people came around, but then my question for you is, what was wrong with that argument? It certainly is the case. There's B1 inhomogeneity on the pulses. The offset effects aren't very good. Why didn't we lose a lot of signal by adding 2 more 180-degree pulses? In fact, if you forget about that, why do any of these experiments work? We have a large number of pulses. If this was like organic synthesis, right? If you have 90% yield in one step of an organic synthesis, and it's 10 steps, by the time you're done, you have almost no product. So what's wrong here? why don't the pulse errors accumulate drastically so that none of these experiments would work that had lots of pulses?
Phase cycling?
Pardon?
Phase cycling.
Well, the phase cycling can eliminate artifacts, but it's not going to recover signal.
There are continuous echoes.
I couldn't hear that either.
These are continuous echoes. I mean, two echoes.
Continuous.
Two echoes, is it? Echoes. Spin echoes.
Spin echoes.
Ah, so again, if the 180 wasn't perfect, that would be a penalty, from the B1 inhomogeneity. So there is a penalty. So if we think the main effect is B1 inhomogeneity, I mean, that was what the argument was. So, if because of B1 inhomogeneity, one part of your sample only sees, say, 170-degree rotation, then more pulses, you're just going to keep accumulating an error, was the argument. But what turns out to be the case is after the first couple of pulses in the sequence, you've lost all the signal from the parts of the sample that are very inhomogeneous with respect to the B1 field. They've dephased, they've gone somewhere else because they didn't see the right amplitude and phase of the pulse. So after the first few pulses, all the rest of your sample is seeing a quite homogeneous field. And therefore you can add more pulses. And that's actually an important feature of how the probes actually work, because otherwise none of this would work, right? If every 180 cost a few, 10% of signal, none of these modern experiments would work. But the first few pulses isolate the homogeneous part of the sample. And from then on, everything behaves close to ideally, which is really fortunate. And eventually we convince. What's that?
How much of the sample is seeing the homogeneous B1 field?
You have to, do some imaging, and it depends, very much on the design of the probe. So that's hard for me to answer. If you do a nutation experiment where you say started with magnetization on Z and applied an X pulse and just kept making that pulse longer and longer, you would trace out a signal. And if you Fourier transform that, you would see the B1 profile. And I haven't done it in a while. They used to look a little bit like potatoes, and they're more Gaussian now. But I haven't done it in a while to really answer that question.
Thank you.
I mean, the B1 inhomogeneity on the solids probe is better because you use solenoid coils. The coil in the solution probe is called the Helmholtz coil, and it's really just a coil of one turn. And as a result, it's not as homogeneous as a multi-turn coil. Now, when we work this out, I worked it out just grinding through lots of product operators. And That's a little painful. It's even more painful to work this out for the Trozy sequence, just grinding through all the product operators. So if we skip on a bit there, so you can look at the product operators. But hold on one second. Hi, I'm teaching. Can I call you back? Okay. Again, it's a case where it's useful to think about the energy level diagram. And here's what we have, for example. Let's suppose we intend to detect I minus. We normally say we detect I minus. So here's a representation of what we want to detect. In what we have at the end of the T1 period is we have an I beta S minus and we have an I alpha S minus. And the minuses, of course, that's IX or SX plus ISY. And we would like to transfer all of this coherence from the S spin over to the I spin I minus. If we did that, we would have transferred both the sine component and the cosine component because that's everything here. And if you look at this diagram, you can see that what we need to do is a pi pulse across the zero quantum transition. Because then this little bit ends here, this little bit ends up there, and we have exactly what we want. But of course, we don't have a transmitter that will do a zero quantum pi rotation. So we have to figure out how to use a combination of pulses and delays to do effectively a pi rotation around the zero quantum transition. And that turns out to be exactly what the sequence does, that I thought up by different means. A picture here. So again, another place where looking at the energy level diagrams is helpful in understanding an experiment that's pretty complicated to figure out if you're just going to crank through all of the product operators. We can add gradients, of course, to this. And then here's the same thing for the Trozy experiment. Now in the Trozy experiment, we don't want to transfer both of these coherences back because this one is the Trozy line and this one is the anti-Trozy line. So we want to transfer all of the Trozy line back, but leave the anti-Trozy line in a state that we don't detect. And now we can fiddle around and see that this now requires two pi rotations. A pi rotation around this transition converts these two coherences into a mixture of zero and double quantum coherence. And then a pi rotation here puts the Trozy line back to detectable signal I minus S beta, but the anti-Trozy line ends up as I plus S alpha, and this won't be detected by the detection operator. So this says we need a selective inversion across the transition where the I spin is a selective inversion of the hydrogens across the transition where the S spin is alpha, followed by a selective inversion across the transition for S spins when the I spin is alpha. And again, we can't do that with a single pulse. We have to sit down and figure out how to do it with a series of pulses and delays, making use of the J coupling. But knowing that this is what we want, that's a relatively straightforward process to then design the pulse sequence. And it's certainly much easier to understand what's happening because I don't care about designing the pulse sequence. I just want to know how it works. This picture is a much more elegant way of seeing how the Trosi experiment works than cranking through a large number of product operators. No questions? Of course, this picture came long after the paper. The first paper by Pravushin, it was basically cranked through the product operators. So the more elegant pictures came later as people thought about the experiment. And there's Trosi versions of all of this, of course. Oh. So having had the idea of 2D experiments, this, of course, can be extended to 3D, basically by overlapping two 2D experiments, where the mixing time of one experiment becomes the preparation time of the next experiment. And the most useful ones are experiments in which the 3D has more or less the same number of peaks as the 2D, but they're just spread out in 3 dimensions to gain more resolution. And that's true of the triple resonance 3D experiments. There was a burst of interest in proton 3D experiments like a nosy, but then the number of peaks in the 3D is more or less the square of the number of peaks in the 2D. So the spectra remain crowded and very complicated to analyze. So that's really not turned out to be a big part of current NMR. So here, for example, would be a nosy experiment. And then the read pulse of the nosy becomes the first pulse of the HSQC. And we have 2 incrementable delays, and then we do 3 Fourier transforms, acquisition, one of the incrementable delays, and then another of the incrementable delays. So there's nothing really new when talking about 3D NMR that we haven't already talked about for 2D NMR. But as you can imagine, the number of possible pulse sequences is very large. And here, for example, in a protein, it's labeled with N15 and carbon 13. We can walk the magnetization in many different ways along the backbone and side chain of an amino acid and then across the peptide bond. The critical thing, of course, is how big are the scalar coupling constants? And one of the more limiting scalar coupling constants then is this 2-bond coupling between a nitrogen and the previous C alpha. And that being only 4 to 9 hertz is limiting for any experiment that relies on that. So that's probably the most important limiting coupling for proteins. There's probably now in the literature over 100 experiments moving magnetization around in these schemes, but probably 10% of those are used very much. So the rest of the next section of this walks through constructing an HNCA pulse sequence. And in the problem set, you were constructing, I think, an HNCO or HNCO. So most of the ideas here would extend over to the problem, with the one issue, of course, that for when you have magnetization on the alpha spins, you have to worry about couplings to the carbon betas, and you might worry about relaxation between the H alpha and the C alpha. So again, because my voice is just about to end, I'll let you look through this. In my way of thinking about it, you can see that I started by splitting an HSQC into pieces. And then, so I'm going to fill in the rest into the middle. Of course, there's other ways to conceptualize it. And we have to worry about refocusing scalar couplings, how we're going to label the C alpha spins. And then at the end of these sequences, when one has particularly long delays because of small couplings, then one has to worry about how should these delays be set and how much relaxation loss might there be. So you end up with transfer functions that tell you how much signal gets transferred through the sequence, and they'll depend on the scalar coupling constants in some way. Here's just a picture of these functions for helix or beta sheet proteins. And you can kind of see that in the absence of relaxation, one might pick values for these delays of somewhere around 25 to 30 some milliseconds. But then in reality, right, there's relaxation losses here. So there's some damping e to the minus r times delta, where r is some effective relaxation rate constant. If you have a guess of it, you can fine tune then what the delay should be. Although you'll see in the literature, people just kind of have rule of thumb about how much to shorten the delays. And I think in the problem set, Stefan just kind of said, pick 80% of what you think is the optimal. Then there's some discussion about phase cycling. Then you can wonder how much we're losing by relaxation. So here I picked a value of the relaxation rate constant to be 30. So one is left with only 20% of the signal. And here's some examples. You can find tables in the literature of estimates of the overall sensitivity of all of these experiments, comparing back to an HSQC experiment. And then you can see why life gets bad. this is a pretty sensitive triple resonance experiment, and we only have 20% of the signal relative to an HSQC. And when you get down to something like a CBCACONH, you're down to a few percent of the signal relative to an HSQC. And then these turn into relatively long data acquisitions. And then there's some pictures for ubiquitin. And I think I just put in a few more pulse sequences just for your reference. But of course, they're all described in enormous detail in the textbook. So I think that's all my voice is going to take today. As I said, we're going to try to get the midterm out to you. I suspect, given my illness, that'll be Monday, not tomorrow. But if you have questions about, the problems so far, either for me or Ann, send emails, and I can always arrange a Zoom to talk to you about the problems. If questions come up that are of general interest, I'll send out an email to everyone with whatever the discussion was.
Is there an answer key for problem set 3?
I think the answer key is primarily a series of papers where the sequence was developed. So I'll dig those out and post them.
Thank you.
Other questions?
Art, for the HNCA, you used an HMQC transfer from nitrogen to carbon. I think.
Right. So in the beginning of these sequences, again, people were nervous about adding more and more pi pulses, so that in the beginning, there tended to be more of these HMQC type transfers. And then in many cases, as people got less worried about the pi pulses, they got replaced by HSQCs. In this case, it doesn't make a great deal of difference because the transverse relaxation of the C alpha, if you have protonated molecule, is dominant. So in this HMQC style, during the periods delta, there's also transverse nitrogen magnetization. So that's adding in its relaxation, but that's small compared to the C alpha. So people wouldn't worry about it so much. On the other hand, in some other sequence, if we were generating multiple quantum of, say, carbonyl and C alpha, those are both pretty large rates. So we might prefer an HSQC type scheme where one of those is on the Z axis so that its rate is smaller. So depends a little bit, of course, on what operators you're talking about, and then the balance of the trouble adding more pulses.
Right. Thank you.
Other questions? Okay, we'll see you next week.
Yeah.